we're gonna toss this up. What the hell? All right, we're doing a sign-in form for you guys today. There we go. Let's just make this all the way. I love how you can see me in the corner. I'm sorry about that. I couldn't get the HDMI cord working. It's my bad. It's my bad. Uh-oh. Oh, shoot. Oh, that's not good. All right. Wow, there's a lot of people here.
Advertising bullets.
Yeah. Also, in that form, there's suggestions for other topics. You can choose up to 3. I just wanted to know what people want to see, because you know, I'm doing it for you guys. It's the main goal.
You should pick GANs. I heard the presenter who would do that is very cool.
You can 100% present. You just gotta ask me, man.
I know.
All right, so let's get some of these new people that came in. What's your name?
Matthew.
Matthew? Matthew. Nice to meet you. What year are you?
Sophomore.
Sophomore? Nice. Oh, what's your name?
Nicole.
Oh, sorry. No, you're good. Nicole, Ariella. It's nice to meet you guys. What are your guys' years?
I'm a third year.
A third year? Ariella?
I'm a second.
Okay, nice, nice. What's your name?
I'm Yehuda.
Another way. Yehuda. It's nice to meet you guys. So does anybody here know anything about machine learning at all yet?
No.
No? Awesome. This is going to be a good lecture then. What time is it? All right, we got 2 more minutes and I'll get going. All the slides in the code that I'm going to be using today is in the YouTube description. So if you guys are on the Discord, just go to the Discord and click on the YouTube link and you can find all the links that you want. Most stuff, I think I'm going to use a Colab today. I'm going to use a space. So today we're going to be learning how to make this demo. It glitches out a little bit because it thinks it needs a graphics card, but it doesn't. Come on, there it is. So today we're going to be making this. We're making a digit predictor where when you put in 2, it guesses 2 for the digit.
Do you use the UFID for anything?
No, it's just to make sure that you're a UF student, basically. Plus, we're probably going to do a Canvas course pretty soon, and we're going to put like people that came to stuff and kind of keep track of it through Canvas.
Okay.
But yeah, that's the goal today. Let's see, we got 1 more minute. Here we go. Okay, let's go back.
What website should we open to start our coding project?
For today?
Yeah.
So the training is done on the Colab, so all the links are down here. You can go down here to the video description. So the sign-in form is here, the Colab is here. This is how I trained the model. What? Oh, okay, you need an account to go on this, I don't know.
Where would I get
But yeah, if you go down here, and then the presentation for today. If you guys ever want to give a presentation on machine learning, go ahead and use it. I don't care, it's free. It's meant for you guys to use. Yeah. So let's get started.
Give it 5, bro.
Give it 5?
Give it 5. I'm sorry. There's always stragglers.
All right. Oh, what's up, Gabe?
This is a packed house.
Yeah, this is a lot of people. Man. To think that it started with me just talking to my desktop at home
I know.
a year ago.
COVID would do that.
Give it
So-
another 5 minutes. What's
In,
up?
Sorry, in this club, do we generally just work in Colab on stuff?
Yeah, so most of the stuff that I do will be in Colab,
Okay.
just because it's easy to share and it works automatically.
And you can copy it.
Yes, and if you go to Colab, you can file download as well. Man,
Ah. Told you.
we'll see.
Told you.
Can you get a picture of this?
Yeah, well, this.
Hold on, everybody say cheese.
Cheese.
Cheese. There we go. Okay. All right, it's been, I don't want to waste people's time.
Sure.
All right, so let's get this show on the road. All right. So today's the introduction to machine learning. Somebody has their sound on. It's okay. My name is Kyle Dampier. If you guys probably know what the GAITOR Club is, it's presented by the GAITOR Club as well. We've got Mr. President right here. First, let's talk about what are ML Mondays. So the whole idea behind ML Mondays is to talk about machine learning lectures. They're both in person and typically streamed on YouTube. There's going to be a recording if you guys want to go back and watch it again. I don't know why I don't want to listen to my voice twice, but that typically follow this general guideline. So first we start off with why. Normally when tools are made, there's a problem it's trying to solve, and the tool is specifically made for that problem. So it's important to understand why that tool works for that problem, so you can recognize times where it's actually applicable. And then we talk about the theory and the reason, the history, or the topic. Next, we talk about the how. The how, it's like a high-level overview of how the topic or the technology actually works. Then we go with the what. The what is basically what tools that you guys can use to use these topics in your actual code and use it to apply it to your projects. So first, let's start off with the types of learning. The types of learning are generally described in 3 ways. The supervised learning, which is task-driven. Oh, you guys can't see it yet. I need to figure out like the timing. And this will kind of include classification and regression problems. Classification is like if you have a bunch of species of dogs, each class is that species of dog. And a regression problem would be like if you wanted to guess the price of a stock in 3 years, because that's a continuous value. A classification is not a continuous value. All right, I'm kind of screwed with this timing. All right, unsupervised. Unsupervised is like data-driven. It's like it includes clustering and association and dimensionality reduction. The third type is reinforcement learning, which we're going to learn from Jim, who just walked in next week. It's how computers sort of learn from errors. It basically helps, it's like the computer's generating the data set. It's trying to find the optimal way to generate the correct data set, which is kind of how Jim described it. It's like playing a game or driverless cars. All right, I think I've got the timing down. All right, so this is the types of machine learning in like a tree format for you computer programmers. But yeah, this is the basic idea. So the agenda of today is, let's go on. What are neural networks? Then we're going to talk about what are convolutions. Then we're going to talk about some different types of applications for convolutional neural networks. And then we're going to go on to using TensorFlow. I've created an entire demo for you guys to go on and see on Hugging Face, and I think it's pretty cool. I showed it sort of in the beginning. It's going to be a very quick overview of TensorFlow. I really encourage you guys to go and look online and go through the code and try and change the layers a little bit. First, now let's talk about what are neural networks. So I'm sure many of you guys have seen this before, but I mean, that doesn't really describe anything. So instead, I like looking at it like this. So don't worry, I'm going to break this all down into its parts. But the basic idea is this is what we're going to learn today. So first off, we have the sort of, I guess you could say input, but it's also like an array of x's. That would be like, for you math nerds out there, it would be like a vector. So you have this list of inputs, and you're trying to find some function f that equals y. So some function x that translates the inputs into some output. So let's put it like that. This timing is really rough, man.
You got it.
So for example, something like an image can be broken down in where each pixel is its own value x inside of that vector. So weights and biases. So the lines are weights in this case, right here. Those basically scale the function. So if you start with a simple y equals x, you're basically trying to scale the inputs using some weight to best fit the output. So that would be like w. So you would have f is equal to w of x equals y. I'm sure you guys have seen that in algebra before. Then you have the red circle bias. This bias is then, it shifts the function left and right. And it looks something like this inside of your equation. Okay. So now let's talk about what is an activation function. So an activation function tries to fit these inputs into, so say your inputs fit to some sort of shape, right? Like so instead of a linear equation, it would be like something like an exponential or a logarithmic sort of equation. This function defines the shape of what function you're trying to fit to. Is anybody confused about that? Because I'll go over it. Okay. So there are many different types of sort of activation functions. So overall, does that make a lot more sense now? Are there any questions before I go on? Yes.
Can you explain the activation function again?
I will go on to the next slide. So the activation function is what you say is what shapes the function. So it's like if you were to plug in instead of like y equals x, it would be y equals e to the x, where the sort of x's are scaled using weights and biases.
Okay, so it's kind of like the model, if you will.
Yeah, it's kind of like the model of how you want to shape your data.
All right.
Yeah, it defines the behavior. So if you notice, like this is basically just what Kyle was saying, is this is just a fancy y equals mx plus b. Instead you have a bunch of m's and you have a bunch of x's. And you take the output of that and you plug it into an activation function, which has they have different properties and they can fit to different data. How we know which activation function's the best for what is just pure experimentation, which is half the fun of machine learning.
Yeah.
But yeah.
And
I'm pretty sure
that's
the
also
activation functions too, they have different ways they treat weights and biases, so
Yeah, that
here's
would make
different
sense.
idea.
Yeah. Well, but that's also why I really encourage you guys to go on and look at my code and play around with it, because it's really fun to just go on and change some stuff and figure out what works better. So here's what a linear activation function looks like, but a lot of you guys would know this better as a regression, where if you try and take this sort of inputs and fit some line to the regression where we find a weight and a bias that gets the least amount of loss. And we're going to talk about a loss function later. Okay. One type of activation function that's really commonly used as a rectified linear unit is basically just takes the max between 0 and your input. This is really good because it kind of makes a cutoff, and that cutoff is essentially the negative weight of that sort of equation. That's how it kind of ends up being. Next, there's tan h. This scales a function between -1 and 1. So say you're trying to do something like a sentiment analysis. You would have a -1 being a really low sentiment and 1 being a really high sentiment, or a positive sentiment. So stuff like that is what this would be used for. And third one, come on, is the sigmoid. This basically scales your function between 0 and 1. So it would be, say you're trying to predict something like a class, kind of like what we're doing today. And there's many more functions. One that I kind of want to mention that's not here is called a GAITOR. it's like, it basically fits like a Gaussian equation. It finds the mean and standard deviation that fits the data best. I think that's a cool function. So here's what changing weights looks like. As you can see, when the weight decreases, it becomes less confident of what it is. So it kind of makes it so it shifts the function up or down. And when the weight becomes higher, it becomes more confident that at that bias, that's where that bias stands. Sort of visually, you can kind of understand it. This is an example of a sigmoid x equals y, weights w. Well, are we gonna go input equals x? I should have just had these going. All right, changing biases. So changing a bias basically just shifts the function. Kind of like in algebra class, I don't know if you guys know why. I'll remember what that looked like, but can anybody tell me why when I have a positive bias, it shifts left, and when I have a negative bias, it shifts right? Because that's kind of non-intuitive. Yes?
Well, you can think of it as like x plus something would equal 0. So then if you want x plus something to be the same value, x has to be smaller.
Yeah, because basically when you're finding y, it shifts over to the other side, and you basically add 5 on both sides or subtract 5 on both sides to get the x. Put x equals y, bias b. So to better visualize this, and you guys, the slides are in here, we can kind of see how a weight affects the movement of the line, and we can see how the bias moves the function left and right. So this would be, so this red one would be a sigmoid, this one would be tan h, and this one would be a ReLU. So yeah, now we're back. So how do we learn these weights and biases? Something called backpropagation. There's many different types of backpropagation. There's like gradient descent. That's the most common. So basically, backpropagation at a very high level is essentially if each dot is one of these epochs, you'd basically define some loss function, which is like your batch, and it's the actual minus the predicted. Loss is equal to the actual minus the predicted, and keep in mind that the predicted is a function, so that means that this is also a function. So then you're able to sort of create this loss function or plane that you can basically take each point, like take point 1 for example, and find the direction where take like a derivative of both these sort of both of the x's, and basically find the direction that it's moving down in the fastest way. Basically, you calculate the sort of magnitude there, and then you move it by some learning rate. And that learning rate is basically like how much that batch weights on your entire data set. And then you change the weights and biases of our function on the derivative of the learning rate. So basically, we change the weights and biases that we sort of started out with, and then we go back and we do it again for the next batch. And then, so a batch in machine learning is like a set of data that defines its own loss function, and an epoch is when each time it goes through the entire data set in trains. So that's kind of the definition of them. So a more realistic loss function would look something like this, where we have like local minimas, but there's one a global minima, and that global minima, so sometimes you'll find yourself getting in these local minimas, and sometimes you'll just get lucky and find a global minima. So yeah, the whole picture. So if we put a lot of these together, we can basically fit any function we want to. And I'll prove it with this next video.
Where did the loss function come from, or is that just an arbitrary graph?
Oh, this is just like, This is just to sort of visualize that like a realistic loss function, it would look something more like this, where it has a bunch of local minimas, and there's like you're not always going to find the global minima, but it gets kind of close.
Yeah. What is that?
I have no clue.
That's
It's
just
just
an
a random.
approximation.
That's just a random thing.
That was good.
So the whole picture. So let's play this. I'm going to speed this up to 2x. All right. So if you guys don't know this guy named CentDex, he's the GOAT. He basically just visualizes these sort of functions. So you can see how so like this is a ReLU function. So this is the bias and this is the weight of those functions. And you can see how he's going to try and fit a sine equation to a neural network. This goes so slow. I'll just let you guys watch it. It's only like a minute long. So you can see how it slowly fits the sine function one piece by one piece. But something to note is that at the end of this sine function, this last linear graph is not going to continue the sine function. So it only understands the data that you give it. Yeah. Move it up. There it is. That was long and drawn out. There we go. Why is it doing that? There, that's close enough, right? So that's pretty cool, right? So there's what's that theorem called, Justin?
It's called the universal approximation theorem.
It's called the universal approximation theorem that basically states that any neural network with any number amount of layers can fit any function. So yeah, what are convolutions? So if you look at how an image is stored, it's just like each pixel has some value between 0 and 255. A color is between 0 and 255 for the red channel, 0 and 255 for the green channel, and then 0 through 255 for the blue channel. So, and in a way, an image is just a matrix, or like a list of numbers. So this is an example of how this dog picture is stored, and you can see the different channels and how they associate. Finally, so this is a visualization I like of convolutions. Basically takes like this little pocket of pixels and gives it like a smaller value, so it's easier to understand. So it's easier to throw it into a neural network, because when you have a neural network and you have like two fully connected layers, the amount of parameters that you have to solve for is exponential, because the more layers you have, the more, because whenever you add one layer or one node, it has to connect to all the nodes that are already there in the next layer. But yeah, here's what a convolution looks like. You have, so for this first one, you have 312, 103, 175, and this is like a filter that tries to find vertical lines. And when you add these together, so 3 plus 1 plus 2 is, I can't do math, 6. And then this row would be 0, and then this one would be negative 13. So 6 plus negative 13 is negative 7. So that's basically, you add all these functions by your filter. And I bet you're wondering why. Oh yeah, sounds familiar. The results are element-wise. We'll get to that. The results of the element-wise product and sum of the matrix. So basically, we're doing more summations and more products. That's basically what machine learning is going forward. Going backwards, a little different. But yeah, let's go on to the next one. So this is what a edge detection filter might look like. You always want the filter. So when you make your own filter, you want all the elements of the filter to add up to 0, because then you're not adding or subtracting anything to the image. You're kind of keeping the same-ish data. So you could probably tell that this is a lot easier for a computer to understand what this means versus what this means. Okay, are there any questions on this? Good, everybody? Sweet. Okay, so yeah, more stuff. Basically, just reiterating what we're doing in a more visual way. And now, yeah, there we go. Okay, so then we go through this filter, and you can see it creates some edges. So that's the result. I don't know why I did this twice. It's my bad. So the difference between machine learning and deep learning typically is that in machine learning you define the filters yourself, so you do all the data processing with the filters yourself. But in deep learning, you're basically solving for the optimal filters for your data set. Right? So you don't have to define your own filters, it basically does it for you based off of your data. Which is a really cool and convenient sort of way to do things. I notice how nobody's in chat. That's unfortunate. Feature learning. Okay, so this is an example of, like, say you have an input of a car. You would have, so like this would be a convolution that is basically solves for each filter using a ReLU, and then you have a max pooling where you have, like, each filter has like a 2x2. I'll actually do I talk about that? What does this do? I do talk about that. Okay. So max pooling is like if you were to have a 2x2 max pooling, it would take a 2x2 square and basically take the max value from that square. So for example, like this square would be that square would be that, and it basically just helps. It basically just helps the bring down the amount of data in the data set, because again we're just trying to compress the data down into some form, into a new sort of output. That being a class or whatever. Yes?
Why wouldn't it take the average? Why would it take the max?
So there is an average pooling. Something like an average pooling would be really good for like a regression, but for something like a classification, a max pooling is a little better. I don't know why there's research on it. I don't know. They just found that out. It's like a normal thing, but there is a layer called a sort of average pooling layer. In fact, if you wanted to, you could go and try it out on the project and just change the max pooling in the notebook to an average pooling. So here's some examples of pre-trained convolutions. These are like pre-trained things that they're trained on a data set of 1 million images on 1,000 different objects. Basically, this one is like an open source one. Where you can just go and then this is the structure. So this is like that first convolution, second convolution, third convolution. Like there's like 6 convolutions, but it turns out really good. It has like a accuracy, 90% accuracy. But this one by Google, which is smaller, has less parameters, but is still 94% accurate, and so on. Like ResNet is about the same. They're both made by Google. But basically the idea behind this is if you don't want to train your convolutions, you don't have enough computing power, you can basically just take these convolutions out as like a pre-processing step and use it for your own model. Because they're already trained on 1,000 images and it has like good sort of, it sort of understands what most stuff is. So this is what VGG19 outputs for this image. Basically, our goal with convolutions is to just make it easier for our computer to understand it through a neural network. We're basically pre-processing the data and sort of extract the features is what the verb is. So here's some applications of CNNs. So this is an example of a typical CNN. Literally means nothing, I just thought it looked cool. Where's this one? So today we're doing image classification. This is like the #1 use for convolutions. There's also, you can use convolutions for facial recognition. You can use convolutions for, we're getting to it, document analysis like OCR. We're kind of doing that today a little bit.
You are.
Kind of, sort
I
of.
say you are.
It's used for autonomous driving. Before there were transformers, people used to train cars to drive based off of convolution, where the input would be like the image, and the output would literally just be step on gas, brake, or turn left or right. There's medical imaging. Hey, Gabe. There's medical imaging, which we're actually going to do a lecture on later this semester. My senior project is finding cancer inside of the pancreas using medical imaging, and then we're sort of taking that segmentation and putting it into a VR headset, so surgeons can help plan out their surgeries faster and more effectively. Then we have biometric authentication, things like Face ID and your thumb. You can basically just predict whether or not whether or not it's the same thumb as the other person, for example. And I mean, does anybody else have any ideas for things we could use convolution for?
Here's a surprising one. So you know those like checkout pages, like credit card checkout, when you like input all your data, they have to detect fraud, right? One thing that they do is they track actually your like mouse gestures and make a heat map for like where your mouse was, and they use that as an image into a convolutional neural network to detect fraud.
That's dope. I did not know that.
Yeah, so I'm working for like this professor for like his research on topological data analysis. There's a thing you can do to like analyze the topology of something, or output like the birth and deaths of like various like homology pairs, which doesn't matter what it is. The point is that like it will give you like coordinate pairs over say like 2,5, like 3,7 or something like that. And then what you can do is you can graph it out on like a 2D plane.
Oh, really?
Yeah. So
That's
what
dope.
someone tried to do, instead of like feeding that data into a network, they graphed it out and they took a picture of that and then fed that into the network.
Oh, that's dope.
And it actually kind of does work.
Yeah, that's awesome.
Yeah.
Something that I've done is I've created using convolutions, because we kind of have a little bit of time here. Using convolutions, I try to create a thing that takes in a thumbnail of a title, like a thumbnail of a YouTube video, and tries to predict the number of views that video is going to get on YouTube. Worked pretty well, actually. It got plus or minus like 10 or 15% on the amount of views it was going to get sort of over time. So let's go on to our example. Okay, I showed you guys a little bit of what we had before, but let's go here. Can it see this? Okay, it can. So this is, yes, so Hugging Face is actually one of our
Kind of partnered with them,
kind of partner. Hugging Face is one of our partners. They basically give us materials and stuff like that to work to help teach people. But they're really good. They're basically used by like Google and OpenAI to like deploy their sort of GPT-3, GPT-2. They're like large language models. They're vision transformers. All their like really modern machine learning stuff.
Another way to think of Hugging Face is GitHub for machine learning.
Yeah, that's a better way to say it. It's like a GitHub for machine learning. That's good. So here's an example. So if I write 3, it was going to give you the probability that it's 3. Or 2, for example. This might not be very good. 2. So that's the basic idea. Yeah, so now let's talk about the notebook. I don't think I can even pull it up on here. Can I?
Scroll up.
Scroll up.
There's the week 1 I got an iPad, yeah.
Oh, but it doesn't show in the, because I can't open Colab in this.
You can.
No, I can't. All right, fuck it. We're just gonna do this. Hello. All right, let's go here. So for the notebook, so here's. Actually, I'm gonna go like this. Can everybody see that okay? All right, so the packages we're gonna use today are NumPy, TensorFlow, Keras, which is just like a TensorFlow live, like a subset of TensorFlow, and then we're going to import layers, which is just another subset of Keras. So the data today came in 10 classes, 0 through 9. And the images that we got, the shape is 28 by 28 by 1. The reason it's not 3 is because it's black and white images. It's only between 0 and 225. And so basically we load and split the data set. So basically this is the data set we're using. Pretty easy to import. Normally data cleaning and figuring out what data you actually want to watch is like 90% of the work. So basically we have the data here, but we split it into 2 subsets. We split it into a training subset and a test subset. And we basically take both X train and X test, and we divide them by 225. Can anybody tell me why we divide them by 225? Yes.
Because you need a decimal, essentially, right?
Yes, because since a pixel's value is between 0 and 255, we divide it by 255 to get the value between 0 and 1. So we're basically like normalizing it. Make sure the images, oh yeah, so basically we're just gonna take our sort of train and test set and add an extra dimension. This is basically to help TensorFlow do some more operations faster. It's just like a TensorFlow thing you have to do. Don't ask me why. I didn't make TensorFlow, so. But yeah, then we print out the shape. So we have 60,000 images that are all 28 by 28, where we have 60,000 train samples. Oh, we have 70,000 images. We have 60,000 train samples and 10,000 test samples. Okay, so this is our model. Can anybody guess what this means? The convolution 2D. Oh, that was unfortunate. Can anybody guess what this value means? This 10. Yes.
How many layers, right? How many convolutional layers?
Yeah. Well, how many filters? But that's kind of the same thing. Yeah. It's basically we're using 10 different filters. And the size of those filters are 3 by 3. And the activation we're using to train those filters is a rectified linear unit. Yes.
So, if you want it to be accurate, you would want more filters in a smaller convolution, or a smaller, like would you want the kernel size to be smaller and the filters to be bigger, or that's not necessarily the case?
It's not necessarily the case. It's so there's something in machine learning called HyperParameter Tuning, where you take a bunch of those values and you try and figure out where like the best possible hyperparameters are. So let's actually talk about what those are. So a hyperparameter would be something like the size of these values, like 10, 33, and something like that. And in machine learning, you can basically find these like the optimal parameters for these. And yeah, so, but not necessarily. If say if you really wanted to make it more accurate, I would probably just get rid of the convolution entirely, but it'll take forever to train.
Mm-hmm. So that would just basically be kernel size 1 by 1, right? Or
It wouldn't even be if you wanted to make this as accurate as possible, I would literally probably just take this out.
oh,
But it would take like 27 times as long.
oh, is that so? If since it's being decreased from a size of 3, it's cubed, or is it because it's?
Yeah,
how
it's
do you
because
get the
it's
number?
because it's 9 by 9, and then you take those 9 by 9s and you make it all down to 1, and then each time you add a new thing, you're adding 10. You're adding what is it? 9. Yeah. You're basically like, say you don't take it down using a convolution. You're basically doing 9 extra pixels per pixel.
So that should take 9 times more, no?
No, because when you add it like, so the way, I'm pulling out the board. So if you have, for example, like 4 layers and you have like 4 outputs, right? If you were to add another one, Oh wait, shit. I butchered this. So if you were to add like another, so each of these are all connected. Oh my god, I suck at this. Okay, so if you were to add another one, you would have to add a new line to every single one of these outputs. So it would technically be more because you have like a matrix operation. It's not just like, because the data coming in, so when it solves it, it's solving for an entire set of data. It's not solving for that one weight, it's solving for n weights.
Oh.
Right, Justin?
Yeah.
Okay.
The stride is not, like the stride is the same size as the filter, right?
What?
If the stride is 1, you're doing it for every like 3 pixels,
Yeah,
right?
I think so.
That's the step. That's how fast you're like traversing. So the whole
Oh.
point of convolutions, I'm just gonna jump in since I feel like we didn't explain it too well, but the point of convolution is to do automatic feature extraction, right? So the
Yeah.
best convolution models and vision models have multiple convolution layers stacked on each other. And the whole purpose is to kind of begin to, kind of like a human, identify kind of key features. So let's say I have a dog and I am a convolution. Well, the first thing I would look is to kind of see the shape. Like, does this object have 4 legs? It has 4 legs? Okay, that's good. And then as you go down each layer, the point of having multiple convolutional layers is to kind of find more finer grained details like as a part of the images. So like I mentioned, like the topmost layer of a convolution would just look at shape, something very general. But the next couple of layers would look at like, does it have fur? Does it have a face? Does it have a tail? And those kind of features are kind of extracted the further down you go in a convolution. So the purpose why we use convolutions and why it was originally invented was because it was designed to provide a mathematical representation for how humans like view and kind of break down like recognition of images and objects. Just like with more math and more like that fun stuff involved.
Yeah.
I'll let you take the wheel.
Awesome. Yeah, so basically, you just have, so this is like each layer, and then this is the number of parameters you have to train for each layer. So you can kind of like see, I guess it's not, I think I did my math wrong, but you were right, I did my math wrong. But still, like 9x longer to go is like,
Much longer.
yeah.
Would it even be longer? It's like you're still parallelizing a lot of the operation.
Well, the thing is, if you're not using a GPU, which I'm not, it's still going to be really slow because it has to do like, he only has like 3 or 4 cores. But yeah, but basically you can, yes.
When we back propagate like a set of data, or not a set of data, a set of weights, is there a formula for how many times for a particular set of data we need to back propagate?
Nope.
No,
There's no
it's up to
formula.
it's up to you really. Go ahead.
I can rant.
Yeah, go for it.
I can rant. Yeah. So I guess we should probably add this to our slide deck. But yeah, a lot of it, machine learning is experimentation, which is why I think it's really fun. Like a lot of software engineering in the classical computer science paradigms are like, build this web app. You throw man hours at it, web app done. A lot of machine learning is like, this works because Jimbo from 90 years ago said it worked. And we just kind of roll with it.
Yeah.
But to answer your question, so a lot of like backpropagation and the sciences behind that is just like best practice, just tips from the experts and what people have done in experiments before and I have like seen success with. And so there's 2 kind of fundamental concepts that I guess I'm going to quickly cover. But you have the bias variance trade-off, which describes kind of the relationship between how long you should backpropagate and when you should stop. So if I backpropagate, for example, for like an infinite amount of time on a set of data, because a neural network has the ability to infinitely kind of match any set of data, that neural network will get it right, and it will get 100% accuracy on this training data that I give it. But if you kind of think about that, that's not really a great idea because you're assuming your training data is going to be 100% representative of what real life is, which it isn't, because the training data is a subset of what we've captured from real life. And so you have finding a good balance between knowing when to stop backpropagation so your model doesn't overfit and just basically kind of memorize your training data, and kind of doing enough backpropagation so your model is able to generalize and know like what the data is. Since you also need to keep in mind that backpropagation is essentially like saying like, how long should this person learn? And for example, if I have like a student and I want to teach him multiplication, if I just give him the same set of like homework and I tell him to grind this one practice problem over and over, he will probably just memorize it at the end of the day. And so for backpropagation, the goal of finding like the most ideal like amount to backpropagate for is to try to minimize like memorization while also encouraging this model to kind of know what it's doing. So finding a good balance between memorization and also being able to kind of learn and like do multiplication in our example. Does that explain it?
Yeah, that makes sense.
Any other questions?
So it's basically up to us to holistically determine where is the equilibrium.
Correct.
Yeah.
So current strategies are to basically kind of keep track of the accuracy. And once your model hits okay, let me back up. So we have two sets of data for this. Let me pull it up. We have, where is it?
Yeah.
Oh my gosh, the delay, like right next to the machine. So we have train and test samples, right? So in the student analogy that I kind of came up with before, the train samples are kind of the practice problems I'm giving the student, and the test samples are, as the name implies, test. Like these are supposed to be samples and kind of problems that the model has never seen before. Because the goal of machine learning isn't to see how well the model does on data it's seen before, it's to test the model on data it hasn't seen before. That's kind of the beauty and kind of the goal of machine learning. And so kind of the most classic strategies that people employ today is they basically train their machine learning model for like a certain amount of epochs, as Kyle mentioned, and then they run through this test sample. They give it this data and they lock the weights of the model so it can't learn off the test data. So based on the accuracy that the model gets on this test data is when you kind of determine when to stop training. Since if you kind of train your model 10 times, for example, and you see that it does like 90% accuracy, like on the test data, like the further you train it, the more the model will try to memorize the, oh my goodness, we'll try to memorize the, there it is. We'll try to memorize the kind of answers from the train data, and that hurts its overall ability to extrapolate and generalize to the test data. So it's basically balancing those two kind of numbers. Does that answer it?
Yeah, this was kind of like what he was trying to explain was over time your accuracy is not really going to increase. So finding like a good place where it's like you like have enough epochs where it's like it's not going to get any better for your accuracy or get any lower for your loss like this. That's the basic idea, and to do that in the least amount of
Just time.
yeah, time and the least amount of parameters as possible. Because the more parameters you have, the more complicated and like more it costs to actually run through the function. But yeah, as you can see here, we have like a 98% accuracy on the test set, which is pretty good. Actually, I'm gonna show you guys what it looks like, how fast it runs, because it's pretty fast actually. And yeah, that's about as fast as if that gives you an idea. That's running on a CPU, not even a GPU, so it's running pretty fast in terms of like how much math it's doing. But yeah, thank you, Justin. Good rant. But yeah, basically something really cool about TensorFlow is that so you can deploy or save your model and the structure of the model by just using model.save, and then that file you can load into anything you want. As long as you give it a 28 by 28 matrix, it will predict something. it'll say whether it's a number, what number it thinks it is. So like if I draw, for example, like a heart in this, I have no idea what's going to come in, but it's gonna guess something, right? So no matter what, you can put in any vector you want, but it's gonna pop out something.
I'm drawing a face.
What if I draw like a smiley face? It's probably gonna come out with 0.
Only a 1.
Like
I'd
very
guess.
complicated, like lifeline.
Oh, it thinks it's a 3. That's interesting.
Gets confused sometimes.
Yeah, it does get confused sometimes because do you see how it kind of thinks that it might be a 3? I mean, I don't know if our test set has 7s like that. I don't know.
I don't think so. The same as 2s.
Yes.
So if it's a function, if we were theoretically to draw the exact same thing, it should have the exact same prediction, right?
Yes.
Pretty much.
Pretty much, yeah.
Yeah, it's deterministic.
Yeah.
So that way you could like try testing for like errors and like repeating errors to see like what could cause, for example, like the 7 with the slash in it.
Yeah, that's actually
Or-
something you
or
typically
0
do.
with-
Something you typically do in real machine learning problems. What happens like when you're evaluating the model, right? So like just mentioned like how for software engineering you like have a problem, build a solution, and that's it. In machine learning, like you have a problem, you build a model to solve it. But actually, it often turns out that it solves like 80% of the problem, but there's this other 20% that you have to do. So for example, here, like it solved most of them, except like for this narrow edge case of like 7s, it's not going to perform well because it hasn't seen those kind of 7s before. It doesn't know to label as 7s. So if you're a machine learning engineer, what you might do is you might collect more data and ask people to draw 7s like that and add it to the training set, split it to the validation set so that your model can increase performance in the real world.
Yeah, and an example of a real-world application that I did this summer. So this summer I worked as a project manager at Dun & Bradstreet. There I was basically like, I had a team of like 5 developers that I managed, and I basically would have, I would have them sort of go to each model that they make. So if you guys don't know, does anybody know what Dun & Bradstreet is? He knows what
You do,
Dun &
like,
Bradstreet is.
Credit scores for businesses and stuff, right?
Yeah, so like if you start a business and you want to get a loan for money, you go to Dun & Bradstreet to get your like a credit score to get a loan, and a lot of businesses have fraud. So basically, there's this model. There's this model that they make that tries to sort of detect fraud, and there's like hundreds of types of fraud. And basically, we would take each type and we would validate that it would find each type of fraud before we deploy it. That's just a real-world example of what he was talking about. Yeah, but I think that's pretty much it. I mean,
Any other questions?
yeah. Is there any other questions? What's up?
So you said that there's 3,380 non-trainable parameters. Are those all hyperparameters?
3,380 non-trainable parameters.
But it's not trainable.
Wait, non-trainable.
Non-trainable. I think those are probably. To be honest, I have no clue.
What are you asking?
Yeah. Wait. In the model.
It says total parameters 23,770, trainable 20,390, non-trainable 3,380.
Not all weights are updated during backpropagation, so those are probably
Yeah.
the weights that aren't updated by the model.
Yeah. So there's something in what's it called when a value gets too small? I forget what it's called.
Vanishing gradient?
Yeah, there's something in neural networks called like a vanishing gradient problem, where if you do enough backpropagation, the amount that it changes is so small that it's insignificant, and there's no reason for you to sort of do the calculation, because it's like very close to 0 when you're adding it on to everything else.
So it's just getting rid of that parameter basically?
Yeah.
Okay.
It might use a batch norm.
What?
Batch norm sometimes does that.
Yeah, that, and it might also be batch normalization, like what he said. It's definitely batch.
It's definitely a part
Yeah,
of
because we don't have enough layers for the vanishing gradient. Now I think about
Does
it.
the vanishing gradient even show up when you do the summary? Isn't there
It's-
like a side effect of
There's a bunch of layers it does.
What?
Sometimes if there's a bunch of layers, it'll come, because like then you're like, it's like adding like 1/16 after 4.
Yeah, but
After
wouldn't
4
that
layers.
only show up like while you're training, not when you're like setting up the architecture?
Yeah, I suppose. I mean,
That's
I have no clue. I forgot I did batch in here. But that was good. That was good. Yeah, if I'm ever wrong, correct me, by the way.
You're wrong. I'm right.
I'd rather give out right information than wrong information. But yeah, I mean, any other questions? Does anybody? Yes.
When you write models.save, so do you need to put, and when you load it, do you need to create an instance so it's created automatically?
Okay, so I'll actually go in and show you what this looks like.
What does it say? Only weights or the whole?
So since it's already in a matrix format, basically the way you go through forward propagate through a neural network, it's just like you're doing matrix calculations. You're not like doing it, so you can just save the matrix and it understands like what the actual model is trying to do. So in this case, we just call models equal to chars.load model, and we don't have to initialize anything because it's just a matrix that we multiply by another matrix. Does that make sense?
And I mean, how does it understand how many there are layers?
Because, well, we don't have to sort of reinitialize because when you save a matrix and you multiply it by another matrix, it's expecting some size back to multiply to the next matrix. So there's like a mathematical reason because like the number of rows and columns always have to match up in a matrix for like when you multiply them. Does that make sense to you guys? Does that make sense?
Kind of.
I mean, essentially what's happening, right? So a machine learning model is just like a sequence of matrices that you multiply by. So these matrices are just numbers, right? You can store them in a file. So this H5 just describes a file format, which it saves all the numbers in the matrices in. And so when you load from that, you can like essentially inject all those numbers when you initialize, instead of like retraining the model again.
Yeah.
And it saves all the layers, not just one fully connected.
Yeah, it saves everything. So it saves like the format and
Yeah.
all the numbers you need.
Yeah, let me
So you could just have to call that one line and you get back what you had before.
I don't know, I mean, I haven't seen the TensorFlow work in PyTorch, and PyTorch you don't have it.
Well, in PyTorch there actually is if you use classes, because when you save stuff in the class structure, typically weights are stored in like a matrix fashion that you can also save to a file. But that's like if you're really into PyTorch, that's like really. But TensorFlow just works out of the box, which is part of the reason why. Well, we use TensorFlow at Dun & Bradstreet for that reason, because like weekly we would update the models. Because like we'd get new data every week, and then we'd have to retrain and do the most updated data. Yeah.
Yeah, this is also, so there's websites online to decompile like the save files for like TensorFlow models and PyTorch models. So if you want to see the structure of like what the computer actually cares about, this is it. And you can also like decompile like far more like complicated models using this. Your mileage may vary, but yeah, also a good tool. It's netron.app. But yeah, any other questions?
By the way, quick poll, like how many of you have like heard of TensorFlow before coming here today? Raise your hand.
Heard of TensorFlow?
Nice. Do you all know how TensorFlow got its name? Like what it is?
That's a good question.
The tensor's flow.
Okay, so
Start spinning, Jim.
Go for it, Jim.
Okay, sure. So basically, think about what is a tensor, right? So let's start from a scalar. A scalar is just a like real number value, like for example 6.3 or negative 2.5. So a scalar is just a number, right? We call this zero dimensional. It's essentially a point. Now, if you get a list of scalars, we call this a vector. So you might have like the sequence of numbers like 2.3 and then 1.7 and then negative 3.2. This would be like a vector with 3 elements. If you expand this into 2 dimensions, then we call that a matrix.
Resources?
Right. So we have this like grid of numbers, and that would be called a matrix in 2 dimensions. Now, what if we do it and extend it to 3 dimensions or more? This would be called a tensor. So a tensor is essentially like a generalization of a matrix to like any number of dimensions. And so in a machine learning model, if you're being very accurate, a lot of what you're performing operations on is not just matrices, which are 2-dimensional, but tensors, which are 3 or more dimensional. And of course, like the computation is often called flow. So it's literally the flow of tensors or TensorFlow.
Yeah.
So yeah, TensorFlow is like Google's original machine learning project. Essentially what they do is they just implement all the like infrastructure you need to like develop models. For example, here you can just tell it, oh, I want like a convolutional 2D layer, right, or a back normalization layer. You could write these all by hand, but it'll take a very, very long time. And so TensorFlow essentially gives you that functionality out of the box so that you can define your model very, very simply, rather than doing everything from scratch. Cool. Any other questions?
All right.
Okay, cool. I thought it might be cool just to talk about filters for a bit, which is something we went over briefly over here. So we can wait for this to run, but
No, Al, shill your workshop thing.
we'll think about how I'm going to do this semester. But anyway, so this is an image in the this is an image in the data set of a 5, right? And the MNIST data set. And what we can do is we can multiply by this convolution filter here, which is an edge detection filter, right? We have 1s in all the edges, and we have a big negative value in the center because we only want the edges and we want none of the centers. So what you can see that happens afterward is that the picture will only detect the edges, and then after you do ReLU, after you do ReLU, which is what our normalization is, you get the image with only the edges. And the reason why this is important is because our model, the initial image has a lot of noise, and our model wants things to be simplified. So if we're able to detect just the edges, we're able to reduce a lot of noise. So if we're able to wait for this to finish, you should be able to play with the filter used and the matrix used. And if you use different matrices, you can detect different filters. So if you try maybe like horizontal values, like 1s in the top, 0s in the middle, and then 1s on the bottom, you'll be able to detect the horizontal edges, or vertical edges, diagonal, however you like. And this is how the model tends to train. And let's scroll. I'm sorry, I'm bad with Macs. Okay.
No, my mouse is on X Games mode.
Mm-hmm. So yeah, this is like the internals of the model. So there's a bunch of different filters that it's looking at. Then you pull it, and then you do it again until you get these very sparse images that only the model is able to actually make sense of. And then the model actually just runs fully connected, like a standard convolution or a standard network. But
that's a cool visualization. And you did this for the?
Yeah, the theoretical club, which we'll see what I want to work on this semester. I think we're just going to work on improving backpropagation and different metrics. And I think we're also going to go over transformer models if that's something you want to look at.
Okay.
But I'll put this code in the Discord and you can play with the filters yourself. If you
Yeah,
want
of
to
course.
see, how that affects the model.
Awesome. Nice.
Wrap it-
I think
wrap
we're
it up,
good.
send it
Thank you
home.
guys for coming. This was a lot of people. Look out.
Oh.
Hopefully you guys learned something new.
Chill this, Kyle.
Oh yeah. If you haven't signed in, please sign in. It's just to figure out what sort of topics we want to do in the future, and get an idea of what sort of group of people we're dealing with.
Aw, Luis. Thanks for the lecture.
Of course. Thank you, Luis, for tuning in, man.
So as I know, you also have some kind of project which